So I wanted to thank Jatine for the invitation to speak and also for making up the title for me. I think he did that in desperation because I didn't come up with one myself. And I just want to remind you that there is no such thing as battery science. It's really just chemistry, material science, and a little physics. And the reason that there's only a little physics means that we're not subject to Moore's law. You know, you have this incredible increase all the time. By the way, my throat's gone. That's why I sound a little funny. But it really is battery chemistry, and that makes it remarkably difficult. And so what I'm hoping to tell you a little bit about in the next half hour is where we are going in the future, not necessarily where we are today, and what things you might be seeing. So I should just thank the people that fund me, NSERC, and the Joint Center for Energy Storage Research, which is in the USA, and BASF in Germany and also in Canada. So when people think about batteries, they often think about the simple things that power most of your devices, but in fact, of course, they're used in many different areas, and there isn't one battery that fits all. There's batteries that are needed to exploit renewable energy resources, in which for storing energy in the megawatt-hour scale. There's ones that we need to power the world, either for large computing, for the internet, for small devices, and so that ranges between the watt-hour and megawatt region. And of course, then there's the enablement of low-cost, high-range electric vehicles, which are still an apple in most people's eye. And in that case, we're storing at the kilowatt-hour region. So the point is that there's many different types of battery chemistry. Everyone thinks of lithium-ion, but there's quite a lot out there. They all have in common the fact that they take chemical energy and convert it to electrical energy. And that is effectively a downhill process, and that's what happens when your laptop discharges. And then when you recharge it, you take that electrical energy and you convert it back to chemical energy. And that's the recharge problem that confronts many rechargeable batteries. So the take-home message of this slide is that these all have different energy needs, and hence they have different materials, and especially they have different cost points. So what works in your laptop is not going to work for the grid. It's just simply going to be too expensive. So since most of you, in fact, I think probably none of you are chemists, this is just a simple little diagram showing how that battery works. So the take-home message here is that it's storing electrons and then releasing them to your device, and then you, as I said, you get them back out of the circuit when you recharge your cell. So because electrons are negatively charged, you need a positive carrier to balance that flow of negative charges, and that is the cation. So this is shown for lithium, but it can be any cation. So the electrons move through the external circuit, and the lithium ions move through the internal circuit, and they match up here at the negative electrode. And when you charge your cell, everything goes backwards. The electrons go back into the positive electrode, and the cations, lithium, whatever, go back into the electrolyte. So the problem in these cells, in other words, the reason why there isn't a better battery, concerns a lot of things, and it concerns the interfaces, because this is actually very, very highly oxidizing, meaning it, like anything else, it'll rip things up. And this is what we call highly reducing, sort of in the opposite direction, chemically speaking. And the electrolyte is typically an organic species. This is the name of it, but you can call it organic solvent. And it's highly reactive at both of these interfaces, but it's what contains these lithium ions along with some counter anion to again balance that charge. So the problems are trying to develop new materials both for the positive electrode, the negative electrode, the electrolyte, and to control the chemistry of the interfaces. And that's where the real challenge comes. So we consider, when we talk about batteries, we call a capacity, how much do we store energy. It's sort of electrons stored per mass, and the cations come along from the ride. As I said, they have to balance the negative charge. So we can quote this in a few different values, milliamp coulombs per gram or coulombs per liter. So we simultaneously need lightweight materials, and we also need dense materials. And that's a real conundrum, because something can't be lightweight and dense simultaneously. So there's an optimization. And then we take that number of electrons stored and we multiply it by the voltage we store it at, we get that value in either watt-hours per kilogram or watt-hours per liter, depending whether we're storing per mass or we're storing per volume. So this is just a plot of where we've come since 1994, because everyone says, oh, these batteries haven't improved. Well, they have. It's just that the devices that they power have been increased and improved in order to balance the extra battery capabilities. So here we are not here in 2014, we sort of sloped over here, but you can see that this line is not linear, and in fact it's curving over to an asymptotic limit. This is data provided by Sony. And this plots the gravimetric, that is the watt-hours per kilogram, versus the volumetric in watt-hours per liter. So there has been an increase in density for these cells. We call them 18650 cells just because it's the size of the cell, and it kind of looks like a huge AA battery. And it is predicted that we're going to hit a limit of about 280 kilowatt-hours per kilogram, which is up here somewhere, very soon. And these batteries are based on what I just described, this process of intercalation where the ions run into between the layers of these materials and then run back out again, sort of like days inserted into a calendar. And the other problem, aside from this limit that we're about to hit, is issues of cost and safety. And that's why electric vehicles, one of the reasons they cost so much, because the battery is a good third of the cost of the vehicle. And of course, safety is a major concern these days. So where we've come from 1990, when Sony first developed its cell, to today and to future developments, span a whole range of different materials that I'm not going to tell you about, but just to point out that they all have different needs and different uses. So aside from cell phones, we now need batteries to power robots. Nobody wants a plug-in robot. We need batteries to power marine vehicles, to store energy for the grid and for cars. It's the Tesla mega factory, and of course, various electric vehicles. So I'll tell you a little bit about where nanomaterials come into the picture. And this is there's a lot of words here, but really I'm only going to talk about these bottom portions. So the materials that you have today, the materials in your batteries work because there are these additives in that electrolyte that deposit on that highly oxidizing positive electrode, and they passivate that interface. And without them, it really wouldn't work at all. So we call these nanolayers at the surface, really important. Tesla and others are trying to switch out the carbon, which is currently in the negative electrode, to new materials that contain silicon nanoparticles. But I'm not going to talk about those because they're too complicated. So I'm just going to talk about a few little things, a few little areas where I see future advances. So Toyota claims that its next move is going to be solid-state batteries, and they claim that they're going to have them in place by 2023. Nobody quite believes them, but it could be the case. This is an article from the Julian Spector just last year in 2017. Another company which went bankrupt but is back on the horizon again, Fisker, promises a 500-mile range, 1-minute charging 2.5 times the energy density battery in no time. So you got to take that with a grain of salt. Peter Dyson, they make vacuum cleaners, you probably know, have also leapt into the solid-state battery fray, prompting this article in the Globe and Mail. Can a company known for making vacuum cleaners make an electric car that doesn't suck? That's not my words, that's theirs. And finally, The Economist, which always has a sensible view of things and a balanced view, asks, will solid-state batteries power us all? This is actually just published about the same time as the Globe and Mail article. And they point out that there's lots of improvements coming, so maybe the answer isn't solid-state batteries, but in fact the article says they probably are. And the reason is basically here. So you take this normal-looking cell with your positive, that's high positive, high redox, high potential, low potential, and you then start to think about the problems of these liquid electrolytes, and as I said, at the interfaces, those organic solvents react. And when they react, they form these very resistive layers that basically then ultimately cause thermal runaway in the cell because you can't get the current to pass through them. So these are serious safety concerns, and it means we can't push the potential of the positive electrode too high, otherwise these organic materials decompose. So is the answer a solid electrolyte? Well, maybe it is. And a solid electrolyte is simply that, a solid which conducts ions. And that may seem surprising to you, but they actually exist. So they have improved safety, and the best thing is that they have improved energy density because effectively you can pack them very nicely. You don't have to hold cells apart for safety reasons. You can make flat packs. And this is where the real energy advantage comes. And they can be used with next generation technologies. And the final really good part is that they display remarkably good low temperature performance, which again may surprise you because it's a solid. But when you think about a liquid electrolyte, when you cool it down, it gets viscous, and that causes massive problems. So these are all the reasons that Toyota, BMW, Mercedes, and a whole lot of other companies are thinking about this. So what is a solid-state cell? Well, it's sort of like the one that I showed you, except that you have a negative electrode, and the electrolyte is this solid, this yellow stuff. So at the negative electrode, you have the active material that transfers electrons, that's the blue stuff, and it's mixed with the yellow particles and some carbon additive. And at the positive electrode, you have your positive electrode material, which is the red, that's at high potential, again, mixed with the electrolyte and some carbon. How do you mix solids together at that intimate level? That's the big problem. So we have an interface. Here's our, say, our active material here, and we want to be able to transport lithium ions and electrons simultaneously at that interface. So that means those interfaces have to be very, very well mixed. And that's where nanotechnology is really necessary to conquer the challenge. So we don't have the reactivity of the electrolyte at the interfaces. Now we have the problem of getting solid interfaces together and making that path length for transport of both of these carriers fairly small. And so that's the big challenge. So there's two ways of approaching it. One is to make new solid-state electrolytes and try to interface them in cells like this, and we call that a solid-state alkali-ion battery, and it can be sodium or lithium. And the other is that we use a metal anode, which really improves the energy density, and then we usually have to put some sort of interfacing ion conductive membrane in place, because usually this electrolyte reacts with lithium or sodium metal. So these are sort of two approaches, and this is what is, I would say, consuming most of our community at the moment, trying to make these work and trying to make these work, and that's sort of where things are going in the next 10 years. So I'll just tell you a little bit about how long it takes for things to actually come into practice. So this is a material which in our field we call LGPS, because it stands for lithium germanium phosphosulfide. And it was reported by a group in Japan, Ryojo Kano's group, in 2011. And it is only coming into the marketplace barely now. So I know you're not chemists, but it's a fairly simple concept. So the first is that these materials actually have a conductivity that is very, very similar to a liquid electrolyte. And that, as I said, if you're a chemist, you find that remarkable, because these ions have to run around in solids. And they do so by having this complicated framework built of these little, we call them tetrahedral building blocks, and they form this rigid sort of parking lot-like structure. And superimposed upon that is this framework of these lithium ion, they're actually bound by sulfur atoms, and the lithium ion literally flow along these channels, along this axis and along this plane. And they flow with a conductivity similar to that of a liquid electrolyte. So Kano's group, working with Toyota, has just published a paper a couple of years ago in Nature Energy, and we know that they've actually done this a long time ago, which shows the ability of these solid-state electrolytes versus the standard lithium ion. So they're higher in energy, sorry for the fuzzy slide here, they're higher in energy, and they're higher in power. And as I said, they have great low-temperature performance. So it took them, well, actually remarkable, only 5 years to take them from in conception into reality, or almost reality. And they're still not, as I said, quite commercial, but they're getting that way. So we're working on similar materials like this with BASF, but we're also working on sodium-ion batteries. And sodium ion is obviously similar to lithium in the periodic table. It's just one down below. Many people speculate that lithium production is going to be compromised in the future, simply because if all of that lithium goes into electric cars, that's about 75,000 tons, which is half of today's lithium production. And that means that ultimately the price is going to go up and we're going to run into issues. So sodium has almost the same potential as lithium. It's just a little bit of a penalty, and there's all sorts of advantages. It's a little bit heavier, but especially for grid storage, it has a lot of possibilities, and obviously it's abundant, whereas lithium is not. So again, I apologize, this is a crystal structure, but the point here is that here's our parking lot. We have a nice framework structure, and it's built of tin and phosphorus and sulfur, and those are nice low-cost elements. And superimposed upon this framework structure, we have effectively the little parking lots, or you can call them conference rooms. And this structure has, just by the sheer forces of nature and good luck, I guess, organized itself so that you have these little chains of sodium ions running in all directions in the crystal structure, along this axis, and in each one of them, we have the equivalent of a conference room that's full and a conference room that's partially empty. So the sodium ions can move from the full room into the empty room, and then next to the full room into the empty room, and basically push themselves along. And it is that structure that gives us almost a free-flowing sodium-ion conductivity, which we are able to envision using computation. We call this molecular dynamics. And so these sodium ions flow in every possible direction in this crystal, and they flow so with a conductivity that's actually very similar to that of the material I just reported by Rio Giocano. It is the highest conductivity in this class of materials, and we've done theory and experiment, which are in remarkably good accord to understand this material better. So we are currently trying to make this into some solid-state sodium-ion batteries in my lab. And this just shows a comparison of the values that we have to those others in the literature. And you can see that both the conductivity and what we call an activation energy are, significantly higher. So, as I said, I don't want to bore you with too much chemistry. So I hope I've convinced you at least that solid-state batteries are certainly a way forward, both for lithium and sodium. The other big thing these days is lithium metal batteries. So instead of using carbon as your negative electrode, you use a lithium metal anode and negative electrode. And that gives you higher energy density for your cell than anything you could possibly imagine. So why haven't we done this already? Well, this is actually what started Canada off in its history of lithium batteries, which many people may not be aware of. So at UBC, they developed a lithium metal battery based in molybdenum disulfide. This was in 1985. And the Japanese loved these batteries so much that they bought them up. They had problems with their pilot plants producing these safely. And ultimately, they ended up in phones, which burned the sides of people's faces. And the company went bankrupt because they got sued. And the problem is that lithium metal or sodium metal grow these nasty things called dendrites. So in the battery, as I mentioned, the lithium ions and electrons have to plate and go back and forth. They have to deposit and redeposit. And in the case of lithium metal, for reasons we still don't understand, they don't do that homogeneously. So they don't do it as a flat surface. And you end up with these little spiky growths, which is what we call dendrites. And they pierce the separator in the cell, and they cause a short circuit. And that's what causes the fire. So since then, we've been struggling with trying to understand how to control this. And I would say that we're on the cusp of understanding. The world, my community, is literally the last few years really advancing this. And one of the places we want to advance it is for lithium-sulfur batteries because they rely on having a lithium negative electrode and a really inexpensive positive electrode. But even if we don't consider sulfur batteries, if we put a lithium metal anode or negative electrode in the normal type of cells that we're using in the Tesla, we would go from an energy density to here all the way up to here, simply by swapping out the negative electrode. So as I said, this is a huge push, and that means that we have to develop protective membranes and interfaces to the rest of the cell. And that's kind of what I would see as the next big push, and as I said, I can tell you that with great confidence because everyone in our community is working on this. We've developed two kinds of materials, two slides, that's it. And we're looking at scalable methods of making these, as opposed to very expensive things. So for example, we've developed really simple chemistry where we simply treat the surface of lithium foil with a metal halide, and it produces what's called an alloy, which kind of self-forms on the surface. And these alloys actually have a diffusion coefficient that's very similar to that material that I just told you about, the LGPS, that solid-state ion conductor. They're in the same ballpark. But these alloys are metallic. And by the virtue of this chemistry, we end up with this complicated interweaving of the alloy and the lithium chloride. And so the alloy allows the diffusion of lithium through the film, and the halide basically makes sure that there is a potential gradient created on that surface that drives the lithium under. So we published this in Nature Energy last year, and it's fast becoming a rather popular topic. And we've also developed other chemical routes to make these phosphosulfide membranes by simple chemistry techniques. And we have a nice, simple, flat, homogeneous lithium flux. And that has allowed us to cycle a lithium cell for 2,000 cycles, as you can see, whereas the unprotected cell dies within a couple of hundred. And again, it's a simple, scalable approach where we just use simple chemicals treated with lithium. I mean, it's not really that simple, but anyway, to create this, as I said, this thin, homogeneous film that allows the lithium ions to pass. So I think I will end off and not talk about magnesium batteries, since, well, I'll just talk about zinc batteries for the last slide. So as I said, it doesn't really make any difference it makes a difference what cation you use, but there's a range of cations. So we're also looking at aqueous zinc batteries. We're looking at zinc because it is a negative electrode that's stable in water, whereas lithium and sodium and magnesium are not. It's also very cheap. It has a suitable redox potential, and it's got good volumetric energy density. And what we're aiming at are trying to develop materials that actually have water in between the layers so that the zinc ion can just sort of move from one watery environment to another. And we've done that with invention of this vanadium oxide cell. And this I'll just end off with a point about how nanomaterials are sometimes critical. So these materials, we grow them as long fibers that are microns long, but they're only 200 nanometers by 50 nanometers thick. So they're like long linguine, or maybe spaghettini or something. And the point is that the transport direction is the skinny direction of these fibers. So they transport the zinc ions really well, and because they have water in between their layers, that facilitates the migration of this zinc ion. And so when we compare our data, which is shown here in red, to the only other two zinc ion type cells that are available, and we're plotting energy versus power, you can see that they're very comparable to this manganese dioxide system, but they have even better power requirements, better power capabilities. And we can cycle these for 1,000 cycles with virtually no loss in capacity, as long as we don't go to full depth, what we call full depth of discharge, at a fairly low materials cost, and at a fairly good energy density, which is about half that of a lithium-ion cell, but we're not using them for cars. We're aiming at this for grid storage. So this is, I think, at least to my mind, a really good example of how nanomaterials make a huge difference. So I'll just leave off on the point that batteries are more predominant and more important than you might think. We always think of, I think a lot of people think of it as a low-tech device, but hopefully I've convinced you they're not. So these batteries can be used to store renewable energy. They can be used to provide storage for cities to make them more energy efficient. And you can think of all those brownouts and problems of that sort. They're also obviously interfaced to electronics and sensing and connect in with autonomous mobility, although I guess maybe that's not the right thing to say at this point, given the problems with that Uber car. But anyway, in principle, those will be overcome. So the innovation in this area really stands predominantly in the materials, but also in the devices themselves, going all the way from small to large batteries. So I'll just thank WISE for the invitation, WIN, which is sort of my home. This is our WIN building, my team especially for all their research, and again, these guys for their funding, and thank you for your attention. I think you said something about glass electrolytes.
Yes.
Ha! Excellent question.
Any work on that at all?
Sorry.
Any work on that at all for glass electrolytes?
Yes. Excellent question. So the answer is yes, we're working on those, in fact, even harder than the crystalline systems. The problem is it's really hard to characterize glasses. So as we joke in my lab, the glasses are what will probably really give you the good conductivity for these electrolytes that you need. And the crystalline materials are what give you the pretty pictures to publish in Nature Energy. So the sulfophosphides that we're working on are actually glass ceramics. So they have little crystals embedded in them. So if you remember that Dow Corning, that white stuff you might have cooked with, or your wife might have cooked with. So that white stuff is a glass ceramic. And they actually have better properties than the pure crystals because they don't have grain boundaries. So that's the other reason that Toyota is so fond of these phosphosulfides as we are, because they form these glasses even more readily than they form the crystalline materials. But as I said, it's hard to understand conductivity in them to some degree. Anyhow.
Thank you. Any further questions? If not, please join me in thanking Linda for a very wonderful presentation. Thank you.